to go through our practice exam for Engineering 110, specifically problem 1 today. I'm your Huckleberry, so hopefully you've seen the movie Tombstone. So, in the movie Tombstone, Doc Holliday is a notorious gunfighter. Any standard deck of cards, there are 52 cards, so 52 distinct cards. So there are 4 suits of cards: clubs, diamonds, hearts, spades, 13 ranks, as seen in the image below. So these are all the possible permutations, all the possible, 52 card deck that you could pull a card from. So Doc Holliday's playing a game. They're drawing cards randomly. Highest card or rank card wins. Doc suspects the player's cheating. Great gunfighter with tuberculosis. He also taken Engineering 110, so he's done statistical analysis. He claims that the player is cheating. So claims the player is cheating. I hope for the other place, let's say Doc's incorrect. Lower the distribution of cards the player drew. So there's a total of 520 cards drawn. They played a lot of games. They also replace the cards in each deck after each draw. So they draw a card, both of them draw a card, they put it right back in the deck. So they drew that 520 times from a single deck of 52 cards. So did the player cheat? Use a 5% significance level. And below here, we can see the number of cards drawn. So let's go look back here for a second. So there are a total of 520 basically cards drawn. 520 cards. So total number of cards that were kind of drawn, or the games basically. So we drew those cards 520 times. So we need to see if the player cheated at a 5% significance level. So what do we know? Well, there are 520, basically this is our total. So the total number of cards that the player drew. So now we can look at, we have our alpha, our significance level is 0.05. And now we need to figure out, did the player cheat? So what we have here is what type of problem? It's going to be a chi-square. So chi-square problem. Why? Because these are our observed values. So observed, or our O sub I. Let's go ahead and put that right here. O sub I. These are our observed values. Now we need to figure out what is our expected values. And once we have those expected values, we can do and calculate and perform our chi-squared analysis. Where remember, our chi-squared experimental is going to be equal to essentially the sum from I equals 1 to k of our observed values, so I, minus the expected values squared divided by the expected values. That's it. So this can be our chi-squared experimental. We're going to do our hypothesis testing. So 1, so our null, so same frequencies. F, our alternative is going to be different. So F's not equal. 3, confidence interval is going to be alpha is equal to 0.05. What type of test is this? Two-tailed, left-tailed, right-tailed? Well, it's chi-squared experimental, so we know that it is a right-tailed test. So we are going to be looking at a falling figure coming up soon. So we need to figure out and calculate our chi-squared experimental. What is this value? And then we need to also figure out, actually we already know this value here, chi, alpha, and nu. So actually let's look at nu right now. So are we being asked if this is a normal distribution? No. So then we know that k minus 1 minus r, if it's not a normal distribution, if we're just looking at similar frequencies, then we know that our r value here is going to be equal to, r is equal to 0. Now, is k 520? This is our total. This is basically like our n, the number of times that that player drew the card. No, it's not. So k is our number of outcomes or variables being considered. So these are our number of outcomes. So 1, 2, 3, 4, 5, 6, 7. So 7 minus 1. So our nu is equal to chi, we're going to look up, squared, 0.05, and then it's going to be 6. So let's actually just write this value down right now. So I'm going to go to lecture 4. Actually, let's go to my presentation. 05, chi squared, 05, 6. So 12.58592. Let's go back here. 12 point over here. So 12.592. So this is our chi-squared experimental, or chi-squared, theoretical here. So remember, right-tailed test, we'll come back to that later. So now let's get to the business of calculating those chi-squared experimental values. So let's go into Mathematica. I'm going to set up my function like this. So my total number of cards drawn, so total is equal to 520. So they drew 520 cards. So what's the probability of drawing? So these are my observed. So observed equals 16, 270, 14, 245, 131, 53, 13. So I need to now figure out my expected values. So what is the probability, again, out of 52 cards? So what is my expected E1 going to be? So drawing a 7 of clubs. So what is that probability there? So a 7 of clubs. Let's go back up to our problem statement. So I want to draw clubs 7. So what is the probability there of finding that value? So I could do 7 of clubs. That is going to be what? Well, it is just going to be 7 of one, 7 of one type, not black or blue. It's just going to be 1 out of 52, right? So let's go ahead and calculate that out right now. Let's go here. Excuse me. So 7 of clubs. So E1 is going to be 1 divided by 52. There's only one probability of pulling that one. And that's going to be multiplied by what? By my total here. So let's get that value right here. What about my E2? So black cards. So what's the probability of me pulling a black card? Well, it's either, as we can see here, you're pulling a deck of cards. The cards are either red or black, so it's half. So that's that probability. So half out of our total. So it's going to be E2 is 0.5 times total. What about E3? Red 9s. So let's go ahead and look back again at our problem statement. So 9 red of them, so they're going to have 2 out of 52. So let's go ahead and look at that right here. So let's go back to our problem statement. So let's go here. E3 is going to be 2 divided by 52 times total. What about E4? So we're looking now at red cards again. So that's the same thing, 0.5 times total. E5 is going to be our jacks, queens, 1, 2, 3, 4, 5, 6, 7. Yep. E5 is going to be our jacks, queens, and kings. So let's look at here. So there's 4 of each of those. So 1, 2, 3. So 4 times 3 is going to be 12. 12 divided by 52 times our total. E6 is going to be what? Black, jacks, queens, and kings. So that's just going to be half of those. So 6 divided by 52 times our total. And our E7, 2 of diamonds. That is going to be the same 1 divided by 52, distinct 1. That's it. So those are my observed. Let me just kind of pull my observed back here. My expected is going to be E1, E2, E3, E4, E5, E6, E7 right here. So I'm going to do my table of my observed of 1 minus my expected of 1 squared, and then I'm going to divide this whole thing divided by expected observed minus this from I from 1 to my length of my observed. Repeat that. So those are my observed minus expected over expected. And again, now I have to sum these. And so that's where the total comes into play. And I get this. So this is my chi-squared experimental. So my chi-squared experimental is 9.375. Chi-squared experimental, this is my value here. Let's go to lecture 3. So I'm going to go to this function here. So this value is going to be my 12.592, and then this is going to be chi-squared experimental, 9.375. So where do I fall? Let's go back to our hypothesis testing protocol. And let's go to the presentation, very last page. So we're doing a right tail test. So we do not reject. So we will do not, this falls into the do not reject region. So do not reject H naught. So let's go back. Oh, excuse me. So we're going to go back to here. So we do not reject our H naught. So the frequencies are, we are not going to accept that the frequencies are different. So we do not reject H naught. So we are saying that the person, luckily for them, they did not, at this confidence level interval, we are not going to say that they cheated. So the frequencies are not the same. So that's it. That's the first problem done. So we're going to tackle the next one, or the next problem, which is going to be a little bit more difficult. You're going to kind of see it's our old friend now, another chi-square test, but this time we're going to look at normal distribution. So more on that in the next video. Thanks. I'll see you all next time. Bye.